we will try to get it figured out. And also let me know if you are having difficulty seeing the screen, and for those of you that are on just the webinar. So I'm going to go ahead and record this, and then we will post it later on. And so to give a brief introduction, for those of you that I haven't met, my name is Nick DiOrio. I work on the SAM team, which is the System Advisor model. And today we're going to be primarily talking about the new battery storage feature in the System Advisor model. And the goal of this model is to integrate PV with storage to evaluate the performance and economic benefit. And so I'll be just briefly walking through some slides and then also doing a demonstration of the beta version that's available, which should be available through the email request for this meeting that you can download and play around with. So just a quick overview of what we're going to be talking about. The model has a few different kinds of inputs. So there's financial inputs, so the cost of the battery system. There's also a fairly detailed technical battery model for both lead acid and lithium ion systems. And so there's some inputs that we'll go over there. And then of probably interest to a lot of you is how do you dispatch the battery to maximize economic benefit. And we'll be exploring the current implementation of the battery dispatch model and also discussing some potential future enhancements. And then a brief validation of some of what we've done, and then, as I mentioned, a demonstration of the model. So what is the battery model in SAM? So it's a techno-economic model that basically allows you to model batteries and their chemistry for different kinds of financial systems, including residential, commercial, and third-party ownership. You can customize whether the battery system is connected on the AC or DC side of the PV system. You can choose between lead acid or lithium ion battery chemistries. And a particularly powerful feature of the model is the ability to do the system lifetime analysis. So one of the main challenges with battery modeling in a PV system is that battery banks degrade depending on how you use them, how you cycle them. And this introduces variable capital costs throughout the life of your system. And so being able to analyze over a lifetime of the system is really important towards capturing the real benefit. There are detailed models, as I mentioned, for the battery chemistry, including things like terminal voltage, capacity, temperature, and then there's a manual dispatch controller which allows you to tailor how you dispatch the battery power. And if you have questions on the webinar, please feel free to type them in, and my colleagues will try to answer them. And I'll also be having a fairly lengthy discussion and question time at the end. So the main financial inputs to this battery model are primarily the battery bank costs, so kind of the cost per kilowatt hour, both for upfront and replacement costs. You can specify the replacement criteria. So with batteries, as they cycle, the capacity degrades, and all of you that have cell phones, you see this after a couple years, your cell phone won't hold a charge anymore, and this is because it's cycled so many times and that capacity is degraded. And so we allow you to select kind of at what degradation level you choose to replace your battery bank, or you can input your own schedule for replacements. You can also look at escalation and de-escalation costs of battery technology. So, with the Tesla Gigafactory, maybe battery costs will get cut in half, and so you could model that. And then, as I mentioned, the system lifetime analysis really allows you to capture the complexity of battery replacements as you use it. So here is a quick look at some of the high-level inputs to the battery performance model. So you basically, within a photovoltaic model, you enable this battery, you basically choose what kind of configuration you have, either DC or AC, and these conversion efficiencies basically allow you to model interconnection losses depending on the configuration. Then you enter the desired bank capacity and voltage, or you can manually specify the cells that you have in series or parallel. And these are kind of the minimum inputs to get started. Here you also have a lead acid or lithium ion technologies, and there are various types of chemistries within those lead acid and lithium ion technologies. And those basically populate defaults and toggle between lead acid and lithium ion models. And so with these high-level inputs, you can get started. Below, which we'll walk through in the demonstration, there are more detailed inputs if you're interested to model those kind of characteristics. I have a question here in the room.
The battery, does that show up if you just run PV now? Or?
No, so, well,
you'll get there.
By default, the battery model is not enabled, but within a detailed PV model, that page is now available, or it's available in the beta version, and you simply have to enable it. Otherwise, it basically will just pretend that there's no battery there.
Okay.
So.
Does that mean it's impossible to have only a battery?
I mean, I suppose you could theoretically have just a very small module such that it's like you have no PV. I'm not quite sure what, yeah, I haven't actually tried that. But,
Zero open circuit voltage or something on the PV.
Right, right. So that's a could be interesting. So we have a just question: is the presentation going to be available afterwards? And yes, we'll go ahead and post this presentation afterwards. So the battery dispatch, currently it's a manual dispatch, so kind of like a time of use schedule. So you can define these custom periods of whether you charge the PV or charge the battery from the grid or PV. Or is it allowed to discharge? If it's allowed to discharge, what percent of the available energy do you want to maximum discharge over that time period? And this gives you a way to kind of tailor and customize a dispatch strategy. And the way that you would use this is look at perhaps a utility rate structure, like a time of use structure for a utility rate, and determine the most economic times of day to dispatch the battery. And so down the road, we do hope to add a more optimized and automated dispatch controller, but for now, this is the solution that we have.
Very quick question for you, Nick. Is the percent capacity to discharge, is that like the delta or is that the end result?
Yes, so the percent capacity to discharge is really meant to be a little more of a tailorable way. So instead of any time that there's a gap in PV and the battery is allowed to discharge, you don't just discharge all the power all at once, like over an hour. So if you wanted to save, you know, potentially discharge some power over a 4-hour period, instead of discharging it all at once, you could say, I only want to discharge 25% of the available capacity every hour. And so that will kind of restrict the duration of the discharge.
So you would define period 1 to be whatever hours, and then you would say 25%, and that would go from, say, 75 to 50. I guess my question is, does it go the delta, or does it go all the way down to 25? Like, is that your
oh no, okay. It's a delta. So yeah, my apologies. And I will walk through in the example a little bit more how to use the schedule, and yeah, and I'll address the questions of how you would use this dispatch a little more clearly, hopefully. And this slide illustrates a little more about what the dispatch controller does and how to visualize what it's doing. And so this top left here, this is a representation of what power source is going to meet the load. So you have power to load from the PV, from the battery, or from the grid. And so you can see here in the peak hours where those green circles are, that's kind of your morning peak and then an afternoon peak. And in those times, the dispatch controller is allowing the battery to discharge, and you see that orange band. And so basically some of the power during the peak is coming from the battery, whereas during the main part of the day, you see the blue, which is basically just the load being met by PV. And then in the evening, after the battery runs out or is no longer allowed to dispatch, you see the load having to be met from the grid. And this, yes.
So is it directed to discharge, or is it allowed to discharge, I guess?
It's allowed. So it's allowed.
So what else makes the decision? If it's 25% for 4 hours, will it discharge 25% each of those 4 hours, or is there other logic?
That's a good question. So it will discharge up to 25%. If there's still excess PV, for instance,
sure,
and the battery is allowed to discharge, it will not discharge.
Okay.
So it will use that PV.
Okay.
Yep. And this bottom left here on the very right where these arrows are, this kind of illustrates that logic. So the battery is allowed to discharge over a 4-hour period, but in this first hour, there's still some PV available. So you don't see it discharging quite as much. Whereas in these last 3 hours, you see a deeper discharge, and that's that full 25%. So as I mentioned before, one of the main benefits and challenges to modeling over a lifetime is the ability to see degradation of the system, and also to be able to capture those costs that have to be incurred. And so in order to capture these costs, you have to have an idea of the dispatch strategy, as well as battery degradation, the replacement criteria, and then the costs. And so in this top right plot here, you see basically the cash flows in the system. And so after about 12 years in this particular scenario, the battery has to be replaced, and you see this large cash flow. And so that's just a quick example of some of what this system replacement model captures. And what you enter in order to get this information, you have to enter a degradation information about the battery. So as you cycle a battery, depending on the depth of discharge, the number of cycles, and other complex things like the calendar life and temperature, the battery degrades at different rates. And so right now we have a user input kind of degradation curve versus depth of discharge and number of cycles, with the idea that you could get at least some of this information from a battery data sheet. And down the road, we would like to add, some more complex models. It's just kind of, there's a lot that goes into it, so it's a challenging model endeavor. This bottom right graph shows basically what I said. So the blue line is the number of cycles, and then this orange line is the battery capacity relative to the original capacity. And so as the number of cycles increases, the battery capacity decreases until the point where it gets down to this 20%, and we replace the battery. And so, oh, go ahead.
One other, sorry to interrupt. The depth of discharge there, 20%, is that you can discharge 20% of the battery. That's not the depth that you go to. That's
correct. So on this degradation curve, these depths of discharges are the average cycle depth of discharge. So if you cycle your battery to an average depth of discharge of, say, 20%, it's going to degrade slower than if you constantly you're cycling it to an 80% depth of discharge. So that's kind of the idea, one of the ideas on that curve as well. Okay, yeah, if it can be clear in some way, please let me know. Just to give you some sense, we did compare a lead acid battery in SAM with the battery model to a lead acid battery in Homer, just to kind of, because they actually use the same chemistry model. And you can see here, basically we can tailor the dispatch and the system to match up fairly closely. So this is basically the state of charge over a few days in a year. One of the main takeaways from this comparison is that the SAM model, which also has a lifetime model and thermal model in it, results in 23% less energy discharged to the load over the year. But disabling those degradation models gives results within about 3% of Homer, illustrating that lifetime degradation is a fairly significant factor. So now I'm going to walk through a demonstration of the model to give you a sense for how you would use it, how you would set up a system, kind of what benefit you could derive from the model in its current state. And so the question that we'll try to answer is, how could I model the benefit of adding batteries to a PV system for a home in Honolulu? So at this point in time, there are potentially only limited use cases for daily cycle batteries in U.S. utility markets, and so it can potentially be challenging to find a case where it might be beneficial. And Honolulu and California might be some of the more interesting places to look at. So what we're going to do, we're going to go into SAM. Please let me know as I bring this up if those on the webinar have trouble seeing this or making it out, and we'll try to adjust if needed. So we'll go ahead and start a new case. Detailed photovoltaic residential model. And as you see here in the left screen, there's now this battery storage tab. We'll just kind of walk down this list, not getting into too much detail, just getting the bare minimum things that we'll need. So we'll set up the system for Honolulu weather. We'll just go ahead and leave the module and inverter alone, which is going to result in about a 4 kilowatt-hour PV system. We're going to go ahead and leave alone the shading and losses. We'll just get down here to the battery storage. And so just click on Enable Battery. For now, we will just assume that the battery is connected post PV after like a charge controller on the DC side, and will be inverted later on. We'll just go ahead and leave the efficiency alone. And some of the battery systems popular battery systems that have come out lately, there's a 7 kilowatt-hour daily cycle battery and about, say, 350 volts, lithium-ion, nickel, manganese, cobalt oxide. And just to give you a sense, here's some of the chemistries you can choose from. So between lead acid, there's various types, flooded, vented, and then there's a lot of lithium-ion cathodes, and then one lithium-ion anode variation. And basically, selection of these changes default parameters that have been extracted from battery references. And so, for instance, if I select lead acid flooded, it will ask me if I want to change the defaults to match, say yes. And so that just kind of illustrates what this does. So a lithium-ion, the lead acid and lithium-ion custom basically just will not populate any defaults for you. And so you can go, and regardless of whatever you choose, you can also tailor the model exactly how you want, so you can enter your own values. The only benefit of these other drop-downs is that, you know, for instance, you know vaguely that the Powerwall might be using an NMC battery, but you don't really have any data about it. You know, you might want to just select that chemistry and then use some kind of characteristic information about another NMC battery. But then if you did find out, oh, the nominal voltage is actually 3.7, you know, you could go ahead and change that. So we won't touch this voltage properties. It's basically depending on the state of charge, the voltage, terminal voltage of a battery changes. And so that's basically what that curve is. We'll go ahead and leave the cell capacity alone. This max C rate of charge and discharge allows you to tailor how much power is allowed to both charge and discharge the battery. So for those of you not familiar with C rates, it's basically a battery specific jargon that scales the currents relative to the capacity. And so we get down here to this computed properties, and we entered a desired bank voltage of about 7 kilowatt hours and cell bank voltage of 350 volts. And so basically what happens is it adds cells in series and parallel until it gets as close as possible to that. So here's where you enter the degradation curve information. So basically, at most battery data sheets, especially some lead acid battery data sheets, have more information on depth of discharge and cycle specific information, whereas lithium-ion battery data sheets might only report one set of information, like after 500 cycles, the capacity is 90%, and it doesn't really tell you much about the depth of discharge. So there's still a little bit of rule of thumb that you might have to, you know, enter in order to fully build this curve. But you can use the defaults, and it can at least give you a rough approximation. So we're going to go ahead and do a lifetime simulation of a PV system in Honolulu. We're going to replace the batteries after they've degraded to 20% of their original capacity. We're going to assume that batteries cost about $430 a kilowatt hour with no escalation. For this manual dispatch controller, let's first go ahead and take a look at the electricity rates. So there's this electricity rates page, which is a pretty handy feature. You can go ahead and just search for a utility. So we'll go ahead and just look up Hawaii Electric Company. And we'll go ahead and select time of use 3-phase rate. So basically this will, depending on the time of day, you'll get charged electricity at different rates. Download that and apply it. Scroll down here. Basically, during the peak evening hours, so 5 to 8 p.m., there's this period 3, which, if we look down here, has slightly higher electricity rates than the rest of the day. And so for a residential scenario, you could imagine if I use the battery during this time, it might provide the most benefit. In a residential utility scenario, you might not be dealing with demand charges or anything like that. And so this would really be one of the few use cases that you could imagine trying to use a daily cycle battery for. So between 5 and 8 p.m., we're going to go ahead and set our controller. For period 3 here is when I have it set to both charge from PV if available, but also to allow discharging. So I just change this period 3 by selecting this schedule, hitting 3. I will just select this 4 p.m. and hit 1. And so now, anytime the PV starts to fade off in the early evening, the battery will start to discharge to meet some of that load. And this period 1 is basically just allowing the battery to charge from excess PV. And getting a few questions about demand charges, which I'll talk a little bit more just right after this. So this is a very simple case. Basically, we're only allowed to discharge the battery during the most expensive time of day, and we're going to see how that affects energy costs. There's also this thermal behavior section, which we won't touch for now, but basically, as temperature changes, battery performance changes. So in very cold weather, batteries don't perform nearly as well as at room temperature. And as they get too hot, they also degrade, which is a feature that we don't currently have modeled, but we would like to as well. A few last things on the systems cost page for the initial cost. We'll also just put in 430 here, just to keep it straightforward. And so this tells us our battery bank is 7.1 kilowatt hours at $430 a kilowatt hour. So an initial payment of about $3,000 uninstalled. We won't worry about trying to model installed costs for now. Go to this lifetime tab, and as I mentioned, battery analysis is really going to be most beneficial over an entire analysis period, so 25 years a PV system or 30 years, whatever you want to model. With this, we'll go ahead and click simulate. Some of the outputs that you get, so these are the main metrics of the system. So battery efficiency, payback period, net present value would be some things that you would look at. To really analyze the benefit of a battery system, you might look at payback period with and without the system. You might run some parametrics on various features of the system to look at that payback period and see when it's most beneficial. So right now it's telling us with this battery system and PV, it would take 8.6 years.
Question on that lifetime, did it actually simulate multiple years, or did it are you just accounting for kind of out year cash flows?
It will do a full time step simulation over the whole analysis period, even down to 1-minute time steps. And so it's a pretty powerful feature. You can get a lot of data.
And that's new.
And that's new.
You can see all the time series for all 30 years.
Cool.
Right. And so you can see for this particular battery with the degradation curve that we had set, it has the battery replacing fairly often, so every 5 years or so, which as you can imagine is going to be fairly undesirable. Can look at some of the time series outputs, and it's kind of scrunched here on the screen, so I apologize. But we can again look at what power is going to the load from various components, so PV, battery, and grid. So we can zoom in here on a day. And there's this handy little feature with the wrench tool. You click stacked area on left y-axis, and it basically gives you the stacked plot, which again is showing you similar to what I explained earlier. We allow the battery only to dispatch between 5 and 9 p.m., and so that's when it's dispatching to meet the load. Another input or another output, we can look at, again, the number of cycles and also the battery capacity percent for lifetime, which is how much it's degrading. So that's where I got that plot before. And so this is over the entire analysis period of 25 years. Every time this orange line reaches the bottom, we replace the battery, and so we start fresh with a new battery. And so that just illustrates some of the outputs. There's more detailed outputs like the actual battery charge and current, voltage, which you can dig into if you'd like. And so the main question we're trying to answer is, was this beneficial? Did this make sense in our current context? So we go back to the summary page. So at 8.6 years, it would take. So let's take a quick look what would happen without batteries, just no battery. Well, it only takes 4.9 years. So what this really illustrates is you have to, it's admittedly going to be challenging in some scenarios to find a case where a battery system is going to make sense. So it really depends on the utility rate structure. It's also going to really depend on how you use it. If you can, for instance, if on this degradation curve, what if we could cycle 5,000 times at 20% before we got that degraded? And what if this was 1,000? We might only have to replace the battery. We might not have to replace the battery. So, you can imagine this brings in a lot of room for developing battery technologies and better cycles of batteries. And so that's kind of an overview of the model with how you would use it, and how you would kind of start to look at utility rates and providing tailorable dispatch in order to meet that. So there was a question about how would you use this for demand charges, and the answer that I'll give is, right now there's really no optimized or automated way to handle demand charges beyond if you have a demand schedule that also has, so for instance, take a quick look at another case that I have here. So for a commercial system, you might have a demand rate utility structure, which I've already downloaded here. So this is in San Francisco. They also have time of use rates, but they're not really tiered in such a way. So here there are demand charges for the system, but they're primarily, they're very flat, so they basically just change from month to month, and depending on the peak kilowatt hours that you use. And so you can imagine if you understand your load well enough, you can tailor the dispatch to try to save some of that peak demand. Unfortunately, right now there's no automated way to guarantee that you're going to always have the battery capacity to shave that. So in this scenario, I know that the load profile over a day looks like a small morning peak with a large evening peak. And so I've tailored the dispatch again to kind of try to discharge over that long period of time in the afternoon where there's the potential to be peak demand. And by doing so, you, of course, reduce demand, but there's potential that you might run out of battery capacity, and then there might be another spike later on. And so it's certainly not optimal from a peak shaving perspective at this point. There are still scenarios where you could still try to model it, but it's also interesting to look at parametric analysis. And so I was kind of messing around trying to find a scenario where a battery system would actually make sense using the current dispatch scenario and trying to understand. So I guess this is going to take a while. But within this commercial dispatch or this commercial utility rate structure that has demand charges, I actually was able to find some cases with this current dispatch scenario where by varying the size of the battery bank as well as how much energy it was allowed to discharge over each time period, I was able to find favorable scenarios where it actually would make sense to put a battery in. So I can only imagine by adding a more optimized or automated control strategy for peak shaving, that benefit would just become more and more apparent. So the main takeaway right now is yes, I can't believe it. Yes, so I think the main takeaway from the current dispatch controller is it's you know, there's definitely improvements that we'd like to make, but it does give you some ability to begin to explore the search space and understand how you might be able to use your battery to derive some economic benefit. And also, it'll be interesting to see how utility rates evolve and which utility rates are actually favorable for deploying these kind of systems and how the battery industry evolves. So it's still the battery industry and batteries for stationary use are still kind of in their early, for grid-connected stationary use are still kind of in their early phase. And so with that, we have still about 15 minutes for questions or comments. So I'd certainly like to open it up and welcome people to ask any questions they have. Okay. So
someone is still unmuted.
Okay. Did we have any? I'm getting some feedback here somewhere. So did we have any questions from the webinar that had not been addressed yet? So can you do different dispatch schedules for the seasons? So yes, via this dispatch page, I kind of made a very simple dispatch strategy over all of the year, but you could imagine, you know, here in the winter, maybe you'd have a different, maybe you'd have a period 4. Then, you know, maybe you'd have that in the fall as well. And so you can get pretty detailed into both the hour of day and the month of year as to when you're going to dispatch. So this kind of allows you to build up schedule for the whole year. So I hope that answers your question.
Got a related question. Do you have a minimum state of charge? Do you have a maximum?
Do you have a minimum state of charge? So right now you can enter that here. I would think I will also add a maximum state of charge, which I hadn't originally considered because, you know, it originally seemed to me like a maximum state of charge, well, you just want to charge your battery to 100%, but that's not always the case, especially with lithium-ion batteries being stored at high states of charge. They actually degrade faster. So
Yeah, most of the systems we've seen in the lab at least 95 is kind of max, sometimes 90.
yeah. So that's a good point. Yeah, that's another.
Further hurts your estimates, probably.
Probably.
I have a question about sub-hourly. Can you remind me, can you do sub-hourly PV simulations?
You can.
And then the battery too, so if you had like a 15-minute peak to full charge, you capture that.
Right, yeah. So I mean, you can enter up to 1 minute data for a weather file. Right now, the battery model will run at that time step as well. The only limiting factor would be these hour schedules. So you can't choose like a sub-hourly dispatch strategy at this point. So that would be the limiting factor.
Solar resource that varied within the hour, right, and the load within the hour, you would capture the demand charges.
Yes.
And of course, you'd enter 15-minute load.
Okay. So the question, when do you expect to, so this might be one or two questions. When do I expect to get out the beta? So the beta is already available. You can download it from the webinar. If you were invited via an Outlook calendar update, there's this link here, and the same link is also available in the general webinar invite that went out. The final release of this, or the first public release, I should say, will be, we're aiming for the 3rd or 4th week of June. So in about 3 weeks, this will be publicly available to download. Probably not substantially different from its current state, but there might be a few improvements that make it in that time. And then throughout the summer and potentially beyond, we'll be continuing to do work on the battery model as we get more feedback and gain an understanding more of what we need to do.
Oh, I want to do that one.
Okay, sorry. So the question is, I assume that the model will replace the battery when it gets to 20% of its original capacity. Can the model add battery capacity before it reaches that level to keep the capacity constant? So the unfortunate thing about battery degradation is that you're never going to be able to really maintain a constant maximum capacity. And to reiterate, this replacement capacity is basically a maximum capacity. So it's 20% of the original maximum capacity. So as you degrade the battery, you know, you're going to have to choose at what point it's no longer acceptable from a performance standpoint. So I hope that gets to your question.
Yeah, I think another question in there might be, so we don't have the ability to add, continually add little chunks of battery capacity in time without replacing the original one.
Yeah, so for instance, I've heard about this, like for a Nissan Leaf, for instance, you might be able to replace some cells in the battery without replacing the whole battery. So if that's the question, then you know, kind of incremental replacements. No, we don't have that currently modeled. So, I'll let, I believe Otto had a question.
Yeah, just, do you plan to build default batteries into there? Like, that would make the, you know, so I'm going to pick a, you know, Tesla.
Right.
To say it.
Sure.
But, you know, there's all these different ones, and then you can just click on that particular one that populates the cycle life and all that kind of stuff.
Okay, so like a battery library from manufacturers?
Yeah, and like, for example, Homer has a default battery library.
Yeah.
That kind of thing. Like you have for PV and et cetera in San Marin.
Yes, we've certainly anticipated that that would be a highly requested feature. And, there is some discussion about doing that, so I don't think that would be for this next release.
No.
But down the road, I think that would be something that would add a lot of value for a lot of people. So, and right now we try to keep it somewhat where you could at least select the battery chemistry and populate some defaults, but that's again not as useful because a lot of battery data sheets, they don't even really say what the exact chemistry is, and so that's a good point. I believe there was another question. Okay. Were there, so any other questions in the room?
Can I ask you a question to Otto? Does the Homer battery library provide you with what you guys typically need?
It's a starting point. You know, the way we use people that do this a lot might pick up some of the one from the default menu, and then when we model a particular battery like you did, then we'll save it as Tesla, you know. So in our library now that we have a particular one, be nice if the SAM user group, when somebody modeled it, could ship it to you so you could add it to the library. It would be a kind of a nice open source way to maybe build that capacity quickly. So sometimes it meets it, but not always, to answer your question.
Okay, because there wasn't an obvious public library that exists already that we found easily. So,
but everybody who uses it is going to build it, and then if they could ship it to you guys, then you could add it to that, make the library. That'd be a useful thing because it's hard to find.
Right. Okay.
What about like standard dispatch strategies? Do you have any plans to add that?
So that would be part of adding in. There's actually a proposal out to get some more funding to develop automated dispatch strategies.
Okay.
So I'm not quite sure exactly what the time frame on that would be, but yeah, we've definitely anticipated that would also be a highly requested feature.
Are you proposing to like research what the best dispatch strategies would be, or just implement what people are most commonly doing, or?
I think it would be implement some of the most common ones.
Okay.
At least from my understanding, I think that's what we would try to do. So.
Is the battery not available from the PV watt module, and is there a reason? It had through the voltages?
It's a good question. So it's not available from the PV watts. Perhaps, Aaron, do you know more about why it's?
It was we picked which one to add it to first, but there isn't a technical reason it couldn't be added in the future.
Okay.
But for the moment, we've chosen not to add it to PV watts.
Yeah. So that would be something that we could also do. Is that the model that you primarily use?
Well, typically, if I'm just screening a site, I don't bother trying to figure out what model panel it might be. That's how it's all wired up.
And in that case, you can just enter 4 or 5 kilowatt size, and the default panel will give you close enough.
Are there more questions from the webinar? CD.
What is the assumption for round-trip efficiency?
So the round-trip efficiency is calculated from the voltage model. So basically, as the battery charges and discharges, the terminal voltage changes and results in requiring more energy to be put into the battery that then can actually be extracted. And so the round-trip efficiency is calculated as the total energy discharged divided by how much energy it required to charge. So does that make sense, or is it a number?
It's calculated. It's an output of the model, not an input.
Oh, yeah. Yeah. So a lot of models will just have an input for round trip efficiency because they're not modeling the voltage variation, and so we model it. It's a little more detailed. You can kind of get to a similar place either way.
There's another question here. Is charging curve, voltage discharge totally dictated by battery chemistry?
To my knowledge, yes. So I'm not quite sure what else it would be dictated by. It's dictated by battery chemistry as well as how fast you discharge the battery. So if you discharge the battery at a very slow rate, the discharge curve will look much different than if you try to dump the whole battery capacity within half an hour.
It might also be slightly affected by the physical build of the battery. Like one manufacturer's battery with one chemistry might have a slightly different voltage curve than another manufacturer's battery of the same chemistry, but those sorts of differences are likely to be quite small when compared to differences between different chemistries. So I'd say the chemistry is the primary driver of the voltage.
Other questions? Comments?
Yeah,
Looks
very
good.
nice.
Thank you.
Yeah, that's good.
Cool.
Keep improving on it.
Yeah.
And as you get an opportunity to maybe use it or try it out, we'd really appreciate any further suggestions and comments you may have as we hope to improve it and release it publicly too.
Nice job.
Okay, yeah.
Thanks a lot.
Thanks.
Appreciate it. Thank you all for coming, and thank you for those that attended on the webinar. And